Imagine it is just past sunset. The familiar stars begin to emerge, pinpricks of light in the deepening twilight. But tonight, a new star appears. It grows brighter, impossibly so, within seconds. It is not twinkling. It is a searing point of light that outshines the full moon, casting sharp shadows on the ground. A collective gasp sweeps across continents as humanity, united in awe and dawning terror, looks up. Then comes the sound. It is not merely a boom, it is a physical force, a wave of pressure that shatters windows 1,000 kilometers away. The ground heaves, a violent shudder that topples buildings and cracks the very crust of the earth. A pillar of incandescent fire and pulverized rock erupts into the atmosphere, a ghastly flower blooming in the sky. The world goes silent, deafened by the concussion. Then, a new darkness begins. Not the gentle dark of night, but a thick, choking shroud of dust and soot that ascends to blot out the sun. The air grows cold. For those who survive the initial blast, the heat, and the shockwave, a new reality sets in. The event we thought belonged only to science fiction, to the ancient past of the dinosaurs. This scenario is not just a nightmare. It is a physical possibility, governed by the same laws of gravity and motion that keep our planet orbiting the sun. To understand this threat, we must first leave the scene of devastation and journey into the cosmic realm from which it came. Let us step back from the immediate shock. Let us quiet the panic and engage our greatest tool for survival, our curiosity. This terrifying spectacle begins not with malice, but with a simple object on a long journey. The universe is a busy, dynamic place, filled with objects in constant motion. Our solar system is not an empty stage with planets set in fixed positions. It is a cosmic shooting gallery. We live within it. So, what exactly is this object that can cause such devastation? What is a comet? Think of it as a cosmic time capsule, a leftover from the formation of our solar system some 4.6 billion years ago. Astronomers affectionately call them dirty snowballs. A comet is a mixture of ices, frozen water, methane, ammonia, and carbon dioxide, all held together with bits of rock, dust, and organic compounds. Born in the frigid, distant reaches of our solar system, far beyond the orbit of Neptune, in two main reservoirs, the Kuiper Belt, the even more remote Oort cloud. There, they drift in the dark for eons, silent and frozen. Their quiet existence can be disturbed. A gravitational nudge from a passing star or a jostle from another object in their cosmic neighborhood can send a comet on a new trajectory, an elongated orbit toward the inner solar system, toward the sun. As it warms, the ices sublimate, releasing trapped dust and gas, creating a coma that can span hundreds of thousands of kilometers. The solar wind pushes out magnificent tails, bright, curved dust, blue straight ion, stretching millions of kilometers, always pointing away from the sun. A comet impact is not a hypothetical event. Earth bears the scars of countless past collisions. Our planet's active geology, its weather, erosion, tectonic plate movements, has erased most of the older, smaller craters, but the big ones leave a lasting impression. We can read this violent history by studying the geological record. One of the most famous examples is the Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico. This is the smoking gun, a roughly 10-kilometer object slammed into the shallow sea there, ending the reign of the dinosaurs. The impact was cataclysmic, energy of billions of atomic bombs, global firestorms, and mega tsunamis. A choking shroud of dust and sulfur blocked sunlight, shutting down photosynthesis on land and in the oceans. Temperatures plummeted. About 75% of species, including dinosaurs, went extinct. In 1908, Tunguska flattened 80 million trees over 2,150 square kilometers. A city killer had it happened over London or New York. Let us break down what would actually happen if a large comet struck Earth tomorrow. At ground zero, unimaginable energy vaporizes everything. The heat flashes rock into gas. An enormous crater is excavated in seconds. A seismic shockwave, more powerful than any recorded earthquake, radiates outward through the crust, leveling structures for hundreds of kilometers. Simultaneously, a supersonic blast wave incinerates and scours the landscape clean. If the impact occurs in the ocean, it spawns a series of mega tsunamis, potentially hundreds of meters high near the site, racing across basins to inundate far-flung coasts. The real global threat comes from what is thrown into the atmosphere, trillions of tons of dust and vapor, plus soot from worldwide fires. A thick veil blocks sunlight. Days darken to twilight, temperatures plunge within weeks, and the cold can last for years. Photosynthesis grinds to a halt, crops fail, mass starvation looms. Phytoplankton die off, food chains collapse. Nitrogen and sulfur oxides drive intense acid rain, an interconnected cascade on a global scale. Given the stakes, it is natural to feel a sense of helplessness, but this is where science offers us power. We are not blind. For decades, astronomers have built a planetary defense system to find, track, and characterize near-Earth objects. Robotic wide-field surveys, Catalina, Pan-STARRS, and the Vera C. Rubin Observatory sweep vast swaths of sky nightly. Repeated images reveal moving points against fixed stars. Detections flow to the Minor Planet Center for follow-up and orbits. NASA's CNEOS and ESA's NEOCC project trajectories and maintain risk lists. We have found over 95% of dinosaur killer asteroids with no foreseeable threats. Yet smaller city killers are harder, and long-period comets may arrive with months to a few years warning. Expanding capabilities, including space-based infrared like NEO Surveyor, means earlier detection and more time to act. The more we look, the sooner we can respond. Finding a comet on a collision course is only the first step. The next, crucial question is, can we do anything about it? Yes. We do not need to blow it up. A tiny change in velocity applied years or decades ahead can make it miss Earth. Several methods can provide that nudge. The most developed is the kinetic impactor. A high-speed spacecraft transfers momentum. Ejecta recoil amplifies the push. In 2022, NASA's DART mission hit Dimorphos and measurably changed its orbit. First time humanity altered a celestial body's motion. A gravity tractor parks nearby and tugs slowly, safer when fragmentation is a risk. For urgent large threats, a standoff nuclear option to heat one side and drive a rocket-like push. Controversial, last resort. Time is everything. The earlier we detect, the more options and the smaller the push we need. So, as we stand under the vast, star-dusted canopy of the night sky, should we be afraid? A healthy respect is wise, but fear is not the answer. The same universe that can birth cataclysm also gave rise to our minds, able to understand and act. We are the first species to grasp the threat and the first to build tools to meet it. A comet's light need not be a harbinger of doom. It can remain what it has long been, a source of wonder, a beautiful visitor reminding us of cosmic grandeur. Planetary defense is insurance. We invest in telescopes, fund research, and test missions like DART, not because disaster looms tomorrow, but to be ready, turning fear into foresight and panic into a plan. The challenge is global, and the response must be too. Open data and shared missions unite us in common purpose. Keep looking up, with curiosity, not anxiety. The cosmos is an amazing place. The sky is not falling. We are learning how to hold it up.